Hey everybody, in 21A, this is a walkthrough review, whatever, of Gravner's practice final. I thought you all might want some more insight as to what is going on this practice test. So yeah, here you go. I'm just gonna, so I don't have the questions written out ahead of time because he didn't provide a blank practice final. So I'm just gonna say them and write them and then we will do them. So let's remember that it's important to read the question carefully. So this question says, please be careful. On each of the parts A through C below, you will receive little or no credit if you make a differentiation mistake, even a small one. So be careful. First one is compute the derivative of the function y equal to the square root of x plus x over x squared plus 1. And I think the first thing we should do is rewrite it as x to the 1/2 plus x over x squared plus 1. I don't want to write that's the derivative. I just want to write that's my function. Let me get this a little bit more centered here. There we go. That's better. Okay. So taking the derivative using the quotient rule, it's going to be the bottom times the derivative of the top. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. Derivative of x is 1 minus the top, x to the 1/2 plus x times the derivative of the bottom, which is 2x, all over the denominator squared. The problem specifically says do not simplify, so we leave it there. 1b. The function given is y equal to the natural log of 4 plus the arc sine of x to the 4th. So just differentiate. It's going to be some chain rule stuff. So the derivative of the natural log of some stuff is 1 over all of that stuff. If you want to write this in a couple steps, you could say it's 1 over all of 4 plus arc sine of x to the 4th times the derivative of 4 plus arc sine of x to the 4th. It doesn't mean you have to write more. And then we could go further and say, okay, now that's going to be still 1 over 4 plus arc sine of x to the 4th times the derivative of 4 plus arc sine of x to the 4th. The derivative of arc sine of x is 1 over the square root of 1 minus x squared. The derivative, let me back that up. The derivative of 4 is 0. The derivative of the arc sine of some stuff is 1 over the square root of 1 minus that stuff squared times the derivative of that stuff. So the derivative of the arc sine of x to the 4th is going to be 1 over the square root of 1 minus x to the 4th squared times the derivative of x to the 4th, which is 4x cubed. I would leave this as x to the 4th squared, but it's also fine to simplify this x to the 8th, which he did do in his solutions. Let's look at the next one. Let me give myself some room here for my papers. So, sorry, I'm dropping things. Part C says find the equation of the tangent line to the curve 2x plus y to the 5th plus xy squared minus y equal to 0 at the point 0, 1. So when you're writing, and then it says give your answer in slope-intercept form. When you're finding the slope of a tangent line or the equation of a tangent line, and your curve is defined implicitly like this, the process is always to differentiate first, and then right after you differentiate both sides, plug in your point. So differentiating some stuff to the 5th, we get 5 times our stuff to the 4th times the derivative of our stuff. The derivative of 2x is 2. The derivative is y. The derivative of y is y prime. Plus xy squared, we're going to have to use the product rule for. The derivative of x is 1 times y squared. Plus x times the derivative of y squared is 2 times y prime. Minus the derivative of y is y prime. Equal to the derivative of 0 is 0. Now we plug in. So x is 0, y is 1. So I'm going to get 5 times, I'm going to try and not write everything here. 2 times 0 plus 1 is 1. I really don't even want to write 1 to the 4th. That seems silly. Times 2 plus y prime. I'm not plugging in anything for y prime. I'm trying to solve for y prime. Plus 1 times 1 squared. Plus 0 times doesn't matter. 0 times anything is 0. I could write 2 times 1 times y prime, but it's really just a waste of ink. That's 0. Minus y prime equals 0. Okay, let's multiply it. So 5 times 1 to the 4th, which is 5. So 5 times 2 is 10. 5 times y prime is 5y prime. Plus 1 minus y prime equals 0. 5y prime minus y prime is 4y prime. 10 plus 1 is 11. Let's bring it over to the other side and say that's negative 11. That means y prime, aka our slope, is negative 11/4. That's our slope at the point 0, 1. And now we can write it using the y equals mx equals b form. I would always start with the y. Oh, well, this one, I will point out, this one's really extra easy in that for finding the equation, they're already giving you the exact y-intercept of 0, 1. So you could just say, I know that y equals mx plus b, but I know since the point it goes through is 0, 1, that it is going to be a b value of 1. Or if you wanted to, you could start with the slope intercept and say y minus 1 equals your slope times x minus 0, and then that becomes that. But you do need to write it in this format if it says to write it in the slope intercept form. Cool. Moving along. Problem 2, some limits. So a reminder for Gravner's class, L'Hopital's rule is in play, so you need to consider possibly having to use L'Hopital's rule. So for 2a, we're finding the limit when x goes to infinity of x plus sine of x divided by the square root of 9x squared plus 1. A couple things here. Often, I don't want to say that really. So reading the directions, compute the limits in any correct way you can. Give each answer as a finite number, infinity or negative infinity. Technically does not exist, should also be an option because there are some limits that just don't exist, even like they're not infinity. Like for example, the limit as x goes to infinity of sine of x just doesn't exist. It's not infinity or negative infinity. Here, what I'm observing is the top is going to infinity plus something that goes between 1 and negative 1. The bottom is also going to infinity. I'm also kind of thinking about the fact that the top looks like it's x to the first, and the bottom is a square root of x squared, which is also like an x to the first. I'm going to show the work a slightly different way than he did. Whenever I'm trying to deal with a square root of x squared kind of thing, I'm going to factor out an x squared from the inside of the square root. I'm going to say x squared times 9 plus 1 over x squared. I'm essentially just dividing each of those terms by x squared. If you distribute that back in, you get the same thing you started with. On top, I'm actually going to factor out an x from on top as well. He divided the top and bottom by x, but I feel like it's a little less obvious what's going on when you divide the top and bottom by x. So here I'm going to get 1 plus sine x over x. Now be careful. It's tempting to say that the limit of sine of x over x is equal to 1, but that's only true if it's as x approaches 0. So the limit as x approaches 0 of sine x over x is 1. Limit as x approaches infinity of sine x over x is not 1. It's actually going to be 0 because of the squeeze theorem. So this is going to equal the limit as x goes to infinity of, so I want to point out here that the square root of x squared is normally the absolute value of x, but here since x is positive, right, it's going to positive infinity, you couldn't be any more positive than that. You just get to say the absolute value of x is x. So I'm going to rewrite this as the limit as x goes to infinity of x times 1 plus sine x over x times the square root of 9 plus 1 over x squared. Those x's cancel, and we're left with the limit as x goes to infinity of 1 plus sine x over 9 plus 1 over x squared. Now, looking at his solutions, it seems like he's very okay with you just saying sine x over x goes to 0. For me, I would do a squeeze theorem argument and say, well, sine x is between negative 1 and 1, divide everything by x, and then take the limit, and oh yeah, this goes to 0, this goes to 0. So by the squeeze theorem, this has to go to 0 as x goes to infinity. So that's going to be 1 plus 0 over 9 plus 0, because 1 over x squared also goes to 0 as x goes to infinity. So you get 1/9. Cool. Let's look at the next one. 2b. So we have the limit as x approaches 0 from the right of e to the x minus 5 over e to the x minus 1. Even though I didn't say it explicitly last time, I kind of did check like what happens when you plug in infinity. I'm getting infinity plus something small over infinity, so I knew it was infinity over infinity type. I could have used L'Hopital's rule here. It would not have worked out well. Like I could have tried to use L'Hopital's rule. It would not have resulted in anything good. So here, if I plug in 0, I get e to the 0 minus 0 minus 5 over e to the 0 minus 1, which is 1 minus 0 minus 5 over 1 minus 1. So if I'm approaching 0 from the right, e to this number slightly larger than 0 is slightly larger than 1. So this really here is a number that's a little bit bigger than 1 minus 1. Right, that's with the 1 plus, that's a number that's slightly larger than 1. And that number is going to be very, very, very slightly positive. I know I should do this because I know that when I plug in my whatever x is approaching and I get a not 0 over 0, the limit's going to be some sort of infinity or possibly not existing if both sides do opposite things. So here you get a negative over a positive, which is going to be negative infinity. And that's really all there is to do here. Let's look at 2c. So for 2c, we have the limit as x approaches 0 of e to the x minus 1 squared over 1 minus cosine of 3x. If we plug in 0, we get e to the 0 minus 1, or 1 minus 1, which is 0, over 1 minus cosine of 0. Cosine of 0 is 1, so this is a 0 over 0 type. And it seems like we should use L'Hopital's rule here. So using L'Hopital's rule, I really do think you should write the L apostrophe H when you use L'Hopital's rule. Still a limit. Take the derivative of the top. Derivative of some stuff squared is 2 times your stuff to the first times the derivative of your stuff, which is e to the x, over the derivative of the bottom, which is going to be 0 minus negative sine of 3x times 3. So positive sine of 3x times 3. If we plug in 0, again, we're going to get 0 over 0. The top is going to be 1 minus 1 over 2 times 0 times 1. The bottom is going to be sine of 0, which is 0. So we're going to use L'Hopital's rule again. Interestingly here, what did he do here? I feel like he might have made a small mistake because it looks like he lost an e to the x when he from this step to the next step. So I'm gonna do it what I think is the right way. I might get a different answer than he actually has in his solutions here. So yeah, that definitely, I feel like that's a mistake because I don't see where that e to the x disappeared to here. Yeah, that's concerning. He does factor out the 2/3, which is totally fine. So you could rewrite this limit as 2/3 times the limit as x approaches 0 of e to the x minus 1 times e to the x over sine of 3x. Use L'Hopital's rule again. The 2/3 hangs out. Constant multiples usually do. Limit still, because we're still taking the limit. On top, I'm going to have to use the product rule. I could have multiplied it out first, but I decided not to. So the derivative of e to the x minus 1 is e to the x times e to the x plus leave e to the x minus 1 alone. The derivative of e to the x is e to the x over cosine of 3x times 3. Yeah, he definitely, he made a small mistake here, which is fine. People make mistakes. It happens all the time. So if you plug in here, you're going to get 2/3 times e to the 0 times e to the 0. Or maybe he didn't. He might not have made it. No, I think he did. Plus e to the 0. No, I think I might have to take it back. Oh well, I thought I found it, but maybe I don't know. Yeah. Anyway, over cosine of 0 times 3. So I end up getting 2/3 times 1, and then there's a 0 there, so times a 1/3, which is 2/9. So I will point out he does have the correct answer is 2/9, but the work he did, I don't know, something looks wrong. I'm not exactly sure what he's doing there, how that like his e to the x is disappearing in the solutions, and I'm not exactly sure why that's happening. Not going to worry too much about it though. So let's look at question 3. Consider the function f of x equal to bx plus 1 if x is less than a, and 1 over x if x is greater than or equal to a. Part A, determine the numbers a and b so that f of x is differentiable for all x. So we want f of x needs to be differentiable, but before you can be differentiable, it also has to be continuous. So to be continuous, we need the limit from the left equal the limit from the right. The limit as x approaches a from the left, we're going to use this piece, and we're literally just going to plug in a for x, and you're going to get ax plus 1. The limit as x approaches a from the right, we're going to use this piece because that's where x is bigger than a, and you're just going to get 1 over a. And then you're going to set these equal to each other. So we're going to have that, you know, I made a small mistake up here, apologies. Limit as x approaches a, bx plus 1 is not going to be ax plus 1. I'm going to plug in a for x. I'm going to get b times a plus 1. Sorry about that. So I should be setting those equal to each other. So I'm going to get ba plus 1 equal to 1 over a. I'd probably multiply I don't know what I would do. Okay, so anyway, we've got that equation. I might manipulate it, I might not. I would probably manipulate it as b times a squared plus a equals 1, but maybe that's not really necessary. To be differentiable, the derivatives have to meet up. So essentially, my derivative f prime, which is b when x is less than a, and the derivative of 1 over x is negative 1 over x squared when x is bigger than or equal to a. So here I need, when I approach a, that the derivative from the left, so b, right, the derivative is always just b on the left side of a, is equal to the derivative from the right side, which is going to be negative 1 over a squared. I'm not showing the same work of taking a limit, even though I could. Interesting. So then we have, well, we can use this now, right? I could go ahead and plug this in right up there, and I could plug it in here. I might rather plug it in here though. So I plug this in for b here. I'm going to get negative 1 over a squared times a squared plus a equal to 1. The a squareds cancel. You get negative 1 plus a equal to 1, or a equals 1 plus 1, which is 2. And if a is 2, go plug that in back here for b, and you get b equal to negative 1/4. He does write out what the function is at the end, but we shouldn't have to do that because he doesn't say to do it. He just says determine a and b. It doesn't say write the function, but the function would be f of x would in fact be negative 1/4 x plus 1 when x is less than 2, and positive 1 over x when x is greater than or equal to 2. And then for part B, it says assume the values of A and B obtained in part A. Assume okay, I feel like the language there is not exactly perfect, it's fine. Assume the values of A and B obtained in A are correct, I guess, maybe. Sketch the graph of the function f using the first derivative. Okay, so I guess we should write our first derivative as well, right? Here's our derivative. Our first derivative is actually b, which is negative 1/4 when x is less than 2, and our first derivative is negative 1 over x squared when x is greater than or equal to 2. I don't know why I would just use this to graph it personally. I don't exactly see how, I know like it's nice to use the first derivative, but really, you know, if you look at 1, 2, and 3, then f of 0 would be 1. And it's a straight line, all the way to get it to 2. F of 1 would be negative 1/4 plus 1, so 3/4. And f of 2 would be negative 1/4 times 2, so negative 1/2 plus 1, which is 1/2. And I didn't draw that very straight, so but it kind of looks like this. And it should be open there. It says it's not open, it's going to be closed because it's going to be continuous. So from the left up until you get to 2, it's just negative 1/4 x plus 1, straight line with a slope of negative 1/4, y-intercept of 1. After 2, it looks like 1 over x. So it kind of looks like, you know, your 1 over x that comes down like this, and then it hits right there, and then flattens out like that. So yeah, kind of a funky graph. My picture is not particularly excellent, but it's all right. Is f 1 to 1? Good question. So, sorry, that was part B. Sorry about that. So is f of x 1 to 1? This is part C. Well, typically the way we show something is 1 to 1 is by showing it's either always increasing or always decreasing, which means we show its derivative is either always positive or always negative. So let's look back at the derivative. F prime of x is -1/4 when x is less than or equal to 2, sorry, strictly less than 2, and it's -1/x² when x is greater than or equal to 2. No matter where we are, it's always negative. -1/4 is always negative. -1/x², well, x² is always positive, so -1/x² is always negative. So f prime of x is always negative, which means f of x is always decreasing. And if something is always decreasing or always increasing, then we can confidently say that it is 1-to-1. Let's look at question 4. In all parts of this problem, the function f is given by f of x is equal to 8 times x minus 2 over x², which he also writes as 8 times x to the -1 minus 16x to the -2. I might even rewrite that as 8 over x minus 16 over x². So there's 3 different ways of writing f. So this is kind of maybe a change or not something that's typical, is we're going to assume the domain is just x being greater than 0. The actual natural domain for this would be that x is just not equal to 0, right? X could normally for this expression it'd be fine if x was negative. So this is actually something that matters. So find some limits. So I want to find the limit as x approaches 0 from the right of f of x. That's going to be the limit as x approaches 0 from the right. I'm going to use this version of it, 8 times x minus 2 over x². And typically when I'm trying to find a limit, I'm just going to plug in. I'm going to get 8 times -2 over a slightly positive number squared, still slightly positive. So it's going to be -16 over a small positive number. Negative divided by positive is going to be negative, and we know when we divide by 0, we get something infinitely large, either negatively or positively. Limit as x approaches infinity of f of x. I will point out, looking at solutions, I feel like if I was grading this, I would not think this person was showing enough work. So if you've looked at Gravner solutions, I would encourage you to maybe show more work than his solutions are showing. Like, for example, the limit as x goes to infinity of f of x. I mean, I guess you can get away with showing less work here. I could either use this version, I'm write it as 8x minus 16 over x². And since the degree on top is less than the degree on the bottom, I can say that's equal to 0. I could also totally use L'Hopital's rule here and say its limit as x goes to infinity of, right, because it's infinity over infinity, of 8 over 2x, and then that's 8 over infinity, which is 0. But I think you should show a little bit of work when you do that. Part B. Determine the intervals on which y equals f of x is increasing and the intervals on which y equals f of x is decreasing. For part B, I think he really does intend for you to use this version of the function to take the derivative to find the critical points. So f prime of x is going to be -8x to the -2nd plus 32x to the -3rd. And then factoring out, I can factor out an x to the -3rd. You always want to factor out the smaller power. -3 is smaller than -2. You can also factor out an 8. So factoring out an 8x to the -3rd, I'm left with a negative x here, because x to the -3rd times x to the 1st is x to the -2nd. And then I'm left with a positive 4 over here. I could rewrite this as 8 over x cubed times 4 minus x. So I set this equal to 0. My critical value is going to be x equal to 4. And now I can kind of see why he made this problem so that it was the domain was x is greater than 0, so that you don't have to worry about the fact that x equals 0, even though it's not a real critical value because it's not in the domain of the original function. It's kind of a place where we usually include on our number line because it's a place where the sign of the derivative can change. So that was kind of a smart thing he did in saying, oh, we're just going to make x greater than 0, so we don't have to worry about 0 being a place where the sign changes of the derivative. So I'm going to do the sign chart like I like to do it. His is fine. I'm just going to do it my way. So this is also why I like to factor this as much as possible, so it's easy to see what's happening here. In my sign chart, where 4 is the only critical value and 0 is the left end, I pick a number bigger than 4, like 5. 4 minus 5 is negative. 8 over 5 cubed is positive. It's negative over here. Pick a number like 1. 8 over 1 is positive. 4 minus 1 is positive. Positive over here. So my function, that's what f prime is doing. So f is increasing, decreasing. Let's go back and read the problem and see what they asked us to do. The problem says, determine the intervals on which f is increasing and the intervals on which it is decreasing. Identify all local max. So I will point out he didn't actually write the words like increasing, decreasing. He just drew a picture like this. It's probably fine. But then we should say we have a local maximum at x equal to 4. He does say to identify all local extrema, so he probably wants you to find the y value as well. The y value would be y equal to f of 4. And we plug 4 back into this, you get 8 times 2 over 16, which is 1. And then we're going to do the same thing except for the second derivative. So I need my first derivative still to find my second derivative. So there's my first derivative. Second derivative is going to be positive 16 x to the negative third minus 3 times 32 is 96. It might be easier to write 3 times 32 x to the negative fourth. Again, we can factor out an x to the negative fourth, the more negative or the smaller power. We can also factor out a 16, which is probably why we didn't need to multiply the 3 by the 32 there. So factoring out the 16 x to the negative fourth, we're left with an x to the first here. Again, x to the negative fourth times x to the first is x to the negative third. And then if we factor out a 16, we're left with, well, 32 divided by 16 is 2. So we're left with a 3 times 2. Or in other words, 16 divided by x to the positive fourth times x minus 6. So we're going to get our critical value of x equal to 6. So now we're looking at the second derivative. Again, 0 should be our left endpoint over here, which I should be more careful about. Pick a number larger than 6, like 7. 16 over x to the fourth is always positive. 7 minus 6 is positive, so positive. And then between 0 and 6, like 1, 16 over 1 is positive. 1 minus 6 is negative. So we are concave down over here, concave up over here. And then finally, we do have an inflection point at x equal to 6. And y would equal f of 6. If we go back to the original function, that's going to be 8 times 6 minus 2 over 6 squared, which is 8 times 4 over 36, which reduces to 8 over 9. Cool. All right. Oh, there's still part, and then the part, oh my goodness, there's the part, this problem goes on and on and on. So part D and E over here. So for part D, sketch the graph. So we have all the pieces. Now we're just putting it on the graph. So let me remind you, I would almost just draw the graph like this. Like, don't give yourself anything left of the y-axis because we know the domain is x greater than 0. And this is part D. And then we found, so we didn't find, but we should note that 2 is an x-intercept because our function was 8 times x minus 2 over x squared. So x equal to 2 is an intercept, an x-intercept. We don't have a y-intercept because x can't be equal to 0. We do have a vertical asymptote, though, and this is actually where it's really good to go back and look at your sign chart for the first derivative. So we look at our first derivative sign chart. It's really good to be like, oh yeah, the function's increasing and then decreasing. So at the point 4, 1, that's our, 4, 1, there's 4. That's our relative maximum. And then at 6, a little bit less than 1, that's where we have our inflection point. So we're increasing, decreasing. Max, and then we decrease, and then we get like that. We do have a horizontal asymptote at y equals 0 because we can't cross the x-axis again because there's no other x-intercepts. And finally, he seems to really like this kind of question. Determine the domain and range of the composite function y equal to the square root of f of x. So notably, I'll point out that the range for f of x is everything from negative infinity to 1, inclusive of 1. And then the domain, well, okay, whatever. So then for y equal to the square root of f of x, which is the square root of 8 times x minus 2 over x squared. I don't think there's any value to simplifying this, right? We don't need to simplify that, but we do need this part to be positive. So looking back at the graph here, we can see that this function f of x is positive once you get past x equal to 2. So here, the domain is going to be that x needs to be greater than or equal to 2, or that from 2 to infinity. The range, on the other hand, well, for the range, we're cutting this part off. So we're basically saying that now the thing we're inputting goes as low as 0 and as high as 1. And you take the square root of that, you're going still from 0 to 1. This question could have been slightly more interesting if this had like a high value of 9, because then the range would be like from 0 to 3 for this one here. But here, the domain is going from the square root of 0 to the square root of 1, which is just 0 to 1. If x is 2, you get 0. 8 times, right, 0 and square root of 0 is 0. If x is 4, you get 1 in here, and the square root of 1 is 1. Yeah, that could have been a little bit, like, if we could make this a little more interesting, I would have had that value be like 4 comma 9 instead of 4 comma 1. So then when you take the square root of it, you get a different range other than the kind of same range, but not exactly the same. Okay. Well, yeah, we did this problem in class, but it's probably worth going over again. Let me do one thing real quick here. All right, so we did this problem in class the other day. You can certainly see a video of me doing it in class, but here it is again. So we have this construction contractor needs to build a small rectangular storage box with a square base, flat roof, and a volume of 16 cubic feet. So here's our picture. Problem 5. And it has a square base. We know we should label these sides x. The height is not related, so we're going to call the height y. And then the roof is this top part here. And they tell us that every square foot of sidewalls costs $1 per square foot. So the front wall is xy square feet. The side wall is also xy square feet. The back wall is xy square feet. The left wall is xy square feet. So the side walls add up to 4xy, and that costs $1 per square foot. So we're going to multiply this number of square feet times $1 per square foot. So the cost for the side walls is $4xy per square foot. And then the cost for the roof, they tell us, is, I believe, $4 per square foot. So the roof, the area is x times x, is x squared, but the cost is going to be $4 per square foot. So that's going to be 4x squared dollars per square foot. So the total cost as a function of x and y is going to be c equal to this plus that, 4xy plus 4x squared. I don't need to write dollars per square foot. We know what the units are. And then we are also told that the volume needs to be 16 cubic feet. So our constraint is that the volume, which is x times y, is 16 cubic feet. And then, as is typical, we take our constraint, we isolate a variable. I'm going to write y equal to 16 over x squared, or if you prefer, 16 times x to the negative second, and then plug that in for y right there. So now my cost as a function of one variable is going to be 4 times x times 16 over x squared plus 4x squared. I would choose to simplify this. I'm going to write this as, yeah, that's fine. Sorry, he wrote something. What is he writing? Oh, he didn't. I don't love. He doesn't show a lot of work. I'm not a huge fan of how little work he's showing here. But I'm going to rewrite this as. I guess I'll leave. He factors out a 4. I don't really. Yeah. So 4 times x times 16 over x squared is 16 over x, or 16x to the negative first. And then I have a plus x squared here. Take the derivative. You get 4 times negative 16x to the negative second plus 2x. And then we're going to set that equal to 0. Well, so again, I want to set equal to 0 right away. He wants to simplify first. So simplifying this, I can factor out, again, the lesser power of x. I can factor out x to the negative second and a 2. So you can have 4 times 2 times x to the negative second. The 4 was already there. negative 16 divided by 2 is negative 8. And then 2x divided, well, and then the x negative second factors out. And then 2 divided by 2 goes away. And then the x divided by x to the negative second is x to the positive third. And if you think about it, right, if you distribute this back in, 4 times 2, or I really say 2 times x to the negative second times negative 8 is negative 16 x to the negative second. And 2 times x to the negative second times x cubed is 2 times x to the first, which is exactly what we have right there. Looking good. Then we set that equal to 0. We rewrite this as 8 over x squared times x cubed minus 8 equals 0. And this part here gives us x cubed equal to 8, which simplifies or solves as x equal to 2. Then, depending on how you want to do this, he looks like he's doing like a first derivative test kind of thing. We know that x should be greater than 0. So looking at the number line for x, I should say for our derivative, here's our critical value of x equal to 2. If you pick a number larger than 2, like 5, positive, positive. Pick a number smaller than 2, like 1, positive, negative. So we are decreasing, increasing, so it's got to be a minimum. So have a minimum cost at x equals 2 feet. And then the y value would be, if we plug back into right there where we have y as a function of x, 16 divided by 4 is 4 feet. Oh yeah, we didn't finish this second part. Assume that the height of the box is restricted to between 1 and 2 feet. With the additional restriction, what dimensions of the box minimize the cost? So now we kind of go back and say, well, if we'd done all this work before, our critical value would have been x equal to 2. We're getting y equal to 4, which is too high. So this value doesn't get considered. So we know that C is, yeah, we have to be, let's write some stuff. So yeah, fair point. This is not a bad question. So we're given that specifically we have this, that y equals 16 over x squared, and that y has to be between 1 and 2. So if we set that right, if we solve for x here, we're essentially saying that x squared equals 16 over y, and 16 over 1 is 16, 16 over 2 is 8. So x squared has to be between 8 and 16, or x is between the square root of 8 and the square root of 16. Square root of 8 is 2 root 2. Square root of 16 is 4. And notably, from our first derivative sign chart over here, 2 root 2 is bigger than 2. It's like 2.8. If we're bigger than 2, the function is increasing. And if the function's increasing, that means the cost is getting higher and higher as x increases. So since C is increasing for x greater than 2, and we want to minimize the cost, we should pick the smallest value of x we can. So we're going to pick x equal to 2 root 2, which then that means y is going to be equal to 2, because when x is 2, well, it's about, right, if x is 2 root 2, y is going to be 16 divided by 2 root 2 squared, which is 16 over 4 times 2, which is 2. Kind of a funky problem, but I like it. Now let's see, how much time do I got here? I don't think I have enough time to finish this right now. So probably have to upload a second video because I need to get going, and there's still, the rest of these problems left are not short. So yeah, I'll upload a second video when I have a chance, sometime later today, and I will cover the rest of these. I probably should have left this problem 5 for the second video, because that's kind of where we get to the more application stuff for the related rates and optimization. But I will upload the second video with problem 6, 7, and 8. And yeah. And then for those of you who are in McDonald's class, I will record a video going over his practice final tomorrow or Monday. I know that final's not until Wednesday, so we got some time still. I know Gravner's final's on Monday, so I thought I should try to get this up ASAP. So Again, I will record the rest of this a little later today. I have to go get my haircut though. All right,